Chapter 16, Current of Electricity, Part 2. Okay, in this section, we will be zooming into what is electromotive force and potential difference. Both of them are very similar and both of them have the same SI units of volts. Okay, but before we move in, to understand about EMF, which is electromotive force, and potential difference, there is some analogy for describing electric current flowing in a circuit in your textbook. So the analogy used in your textbook is like your circuit is actually like this water pump system. So the water that is moving in the water pump system is the charges that is moving. And then the battery is the pump that pumps the water up so that the water can flow down, okay, from a place of higher gravitational potential energy, drop down to a place of lower potential energy. Okay, and EMF is actually the pumping action of the pump. So in the energy in the chemical potential store of the pump is transferred to the kinetic store of the water or the electric charges as it flows through the circuit. But I didn't really like this analogy, so I'm going to give you another analogy. So another analogy is like a roller coaster. Okay, so in your roller coaster, you need to have an electric belt to bring the roller coaster right up to the top. So when I'm at the highest point of the roller coaster, I have the highest amount of gravitational potential energy. And if I were to release the roller coaster at this point of time, it will just move down the entire track, okay, until you reach the end of the track, which is a place of lower gravitational potential energy. So we can think of the part where it's moving up by the electric belt as the battery. So the battery actually gives it the energy to move up all the way to the highest point. And at the highest point, we call it the positive terminal of the battery is at high potential. In batteries or in circuit, we don't use gravitational potential energy. We just say that it's at high potential. Okay, and then once it passes through this reach this high potential, the charges will flow all the way to it reaches back to the battery, the negative end of the battery, which is at low potential. So charges always flows from high places to low places, or high potential to low potential. And then once you reach the low potential negative side of the battery, this battery will supply it with energy, okay, in order to pump it up again to high potential. Then the charge can move again across throughout the entire circuit, which is across the entire roller coaster track. Okay, so what exactly is electromotive force? In short, we call it EMF. It usually refers to the source, okay, not a component, but a source. In this case, usually it's our battery. The battery is the source that gives it the energy for it to move throughout the entire circuit. So the electromotive force, EMF, of an electrical source is the work done or the energy given by the source to drive a unit charge, which is 1 coulomb, around the whole circuit, because the battery needs to have sufficient energy for the charge to move across the whole circuit. Okay, so my formula over here is slightly different from your textbooks. Your textbook is E equals to work done over charge. But I don't want to use so many formulas because under potential difference is V. So I just convert everything to V equals to W over Q, whereby V is the potential difference or the EMF, and which is measured in volts. That's why I use the symbol V. And then work done is actually the amount of energy given by the source for each charge, or the work done to move each charge. So energy and work done is the same, it's in joules, and Q is the charge, which is in coulombs. Or you can remember by this triangle, WVQ. So SI unit for EMF is volts. Okay, so what does it mean? If I have a battery of EMF 10 volts, okay, it simply means that for every 1 coulomb of charge that passes through my battery, okay, it will be given 10 joules of energy. Okay, and this 10 joules of energy is sufficient for this 1 coulomb of charge to move throughout the entire circuit. Okay, so in short, EMF of 10 volts means 10 joules of energy is needed to drive 1 coulomb of charge around the whole circuit. Okay, so in our normal batteries, it's only 1.5 volts. So which means that every charge that passes through, it gains 1.5 joules of energy, which is sufficient for it to move across the entire circuit. Okay, let's go into work examples. You may pause the videos as I go through the work examples and think about the answers first. Okay, I'm going to go through now. The EMF of dry cell is 2.2 volts. What is the energy dissipated by the cell in driving 0.6 coulomb of charge around the whole circuit? Okay, so I am interested in energy, which is also work done, which is W. So W is V times Q, so it's 2.2 times 0.6. I get 1.32 joules. Okay, the energy of work done. Next, what is the EMF of a cell if it uses 4.2 joules of energy as it pushes 6 coulombs of charge around a circuit? Okay, so in this case, I am interested in EMF, which is volts, which is V. Okay, so V equals to work done over charge or energy over charge. So it's using 4.2 to push 6 coulombs. So it's 4.2 divided by 6. I get 0.7 volts. Next, cells can be arranged. Your cells is actually your individual so-called like battery, okay? But by right in physics term, battery means multiple cells together, okay? The EMF of an electrical source depends on the arrangement of the cells, okay? So the cells can be arranged in either series or it can be arranged in parallel like this. Okay, so in series, the charge will pass through the first cell and the second cell. So in the first cell, I have 1.5 volts. I will have gained 1.5 joules of energy for my charge. And then I still pass through the second cell. I will again gain another 1.5 joules of energy. So for each charge that passed through these two batteries, it will have gained 3 joules of energy. So the entire EMF, okay, of batteries in series is actually the sum of the individual cell. Okay, so it's 1.5 plus 1.5 volts. But if I put it in parallel, what happens is charges, when I come over here, my charge will split. Some charge will go to the top and some charge will go to the bottom. Okay, but each charge will only pass through one battery. So each charge will only gain 1.5 joules of energy. So I'll gain 1.5 joules, and then this charge also gain 1.5 joules. And when I combine back, I got more charges, but each charge will still only carries with it 1.5 joules of energy. So the resultant EMF will be that of a single cell only. No matter how many batteries I connect in parallel, I will only have 1.5 volts. Okay, next we move on into potential difference. Okay, there's a slight difference between EMF and potential difference. Potential difference is a term used across components in a circuit. It can be through a light bulb, it can be through a resistor, or anything in a circuit. Okay, so potential difference is defined as the work done to drive 1 coulomb of charge through that component. It's not through the whole circuit. Okay, it's just through that 2 points where you want to measure the potential difference. Okay, so it's the same formula and the same SI units, volts. Okay, so a PD of 10 volts, potential difference, we use short form is PD. A PD of 10 volts across a component like a light bulb simply means every 1 coulomb of charge that pass through, I need 10 joules of energy to move it across the component. So means 10 joules of energy is needed to drive 1 coulomb of charge across that component. Okay, so you can read the word examples. If a charge of 3.6 times 10 to the power 4 coulombs pass through an electric heater and the amount of electrical energy converted into heat is 7.92 megajoules, calculate the potential difference across the ends of the heater. So I'm interested in potential difference, which is V. So V equals to work done over charge. The amount of work done or energy is at 7.92 megajoules. So it's times 10 to the power 6 over the amount of charge that flows through, which is 3.6 times 10 to the power 4 coulombs. So I get 220 volts. 220 volts means every 1 charge that passes through this heater, I need to give it 220 joules of energy to move it across the heater. Next work example. Okay, in this diagram, there is a Van de Graaff generator. It is used to discharge. It's allowed to discharge through this metal ball. And then the discharge current that flows through this metal ball down to the ground is 0.01 ampere. The potential difference between the generator and the ball is 100 kilovolts. The discharge takes 1 millisecond. What is the energy of the discharge? So I'm interested in energy, which is work done. So I need volts and charge. But I do not have charge. I only have volts. So I need to combine the first equation, whereby current is rate of flow of charges, okay, and the second equation. So the amount of charge Q equals to IT. So I have a current of 0.01 that flows through in 1 millisecond. Milli is times 10 to the power minus 3, so I can get the total amount of charge that is flowing by in this 1 milliseconds, which is 1 times 10 to the power minus 5 coulombs. And then after that, I want to get the energy, which is work done. W equals to VQ. So the voltage, 100 kilovolts, okay, times the amount of charge, 1 times 10 to the power minus 5. Okay, and then I get 1 joules. Okay, so the term EMF is usually used for electrical source. It's the amount of energy provided by the source, the battery, to drive the charge across the whole circuit. While potential difference is just the amount of energy needed to move across that component. Okay, so EMF is present even when there is no current drawn from the source. So we always say a battery, even though it's not connected to any wires, there is still an EMF of 1.5 volts. Okay, be it I have a complete circuit, I don't have a complete circuit, the battery itself just stands alone will already have an EMF with it. Okay, but potential difference will be 0 if there is no current flowing, because if there's no current flowing, my charge don't need any energy to move across that component. My charge is not even moving. Okay. Okay, next, how do we measure potential difference? We use a voltmeter. So your voltmeter looks like this. It looks exactly the same as an ammeter. The only way to differentiate them is for ammeter is an A in the center, and for voltmeter is a V in the center. Okay, or we can use a multimeter. But again, as what I say, for O-level, you need to use a voltmeter. So voltmeter is slightly different from ammeter. Voltmeter is connected in parallel because voltmeter has got very, very high resistance, unlike ammeter. If I were to put my voltmeter beside my light bulb, because of its high resistance, my charges cannot flow through it, so it will affect my light bulb. My light bulb will be very, very, very dim, or even it will not light up because the resistance of the voltmeter is too high. Okay, so it must be connected in parallel. So when it is connected in parallel, and because of the high resistance, the current would not want to flow through this voltmeter. All the current will just flow through the light bulb and back to the circuit. Okay, and back to the battery. Okay, it has high resistance because it doesn't want current to flow through it. It doesn't want to affect the circuit at all. Okay, and again, positive terminal, you can take a look. This is the positive terminal of the battery. It must be connected to the positive terminal of the voltmeter. Okay, so you can see all the red wires is connected to the positive terminal, and all the black wires is connected to the negative terminal of the battery. And again, if you connect wrongly, the needle will go below the 0 marking. So just swap the connections to the voltmeter. Okay, so if I want to measure the EMF, okay, I will need to connect the voltmeter parallel to the battery. So I use 2 separate wires out of the battery, the plus side to the plus side, the minus side to the minus side, like this. I form a separate loop. This is connecting in parallel. Okay, I can put it beside the battery. I just form another loop out from the battery. Okay, and if I want to measure across the potential difference across a light bulb or any 2 points in the circuit, then I will need to put my voltmeter parallel to the component that I want to measure the potential difference. So in this case, I want to measure potential difference, how much energy is needed to move one charge across this light bulb. I will put my voltmeter in parallel across the light bulb like this. Okay, next, let's go into certain misconceptions. Okay, you may read the concept cartoon. 1 minute ago, the light bulb is still light up. as seen in this diagram. Then after that, a few seconds, 1 minute later, you will see that the light bulb goes off. So this boy was saying the bulb is not lit as the electrons inside the batteries are being used up. The battery becomes empty. Next one, the girl said, I think it's because the energy from the battery is being used up by bulb. And no, the other guy was saying, no, the battery is flat because the electrochemical reactions inside the battery has depleted the material. So the question is, why do you think eventually the battery will go flat after using it for some period of time? Okay, is it because there's no more charges? There's no more energy inside the battery, or is it because the reaction cannot occur inside the battery as the material has been used up? Okay, so some of the common misconception over here is the first guy is wrong because electrons are not being stored up in the battery. Okay, this one we have mentioned in the first part. Electrons are already present in the wires, in the light bulb, and everywhere. Electrons are not, or charges are not being supplied, doesn't come out from the battery. Okay, so electrons that flow through a circuit originates in the wires of the circuit already. The battery supplies energy to move the electrons, not supplying electrons or charges. Okay, and then for the second girl say, oh, because the energy in the battery has been used up. Okay, but we learned that under principle of conservation of energy, energy cannot be used up. Okay, the energy actually gets transferred from chemical potential stored in the battery. Is transferred electrically to the internal store of the filament to light up the light bulb. So energy is transferred from the battery, okay, to the internal store of the filament for the filament to light up. It doesn't get used up. So the second girl is also wrong. Okay, the third guy is actually correct. Okay, because in the battery there are chemicals for a reaction to occur, and this reaction generates electricity. It produces ions to move. Okay, it produces the electrical energy. So a battery goes flat because the materials inside the battery has been used up. Okay, so there is no more reaction that can goes on, and no more reaction, no more electricity can be produced. Okay, so next you can take a look at this picture. Okay, so you can think of the battery or the voltage as the energy source to push the charges across. So if I have a high voltage, means I have a lot of energy, okay, given to each charge, the charge can move through very fast. But if I have low voltage, means I have very little energy given to each charge, then the charges will move very, very slowly. Okay, so I'm going to share with you over here. You can take a look at the previous simulation I have again. So if I close the switch, okay, the battery is the voltage. So over here, the voltage is 6 volts, meaning every one charge that pass through, I'm going to give it 1 coulomb charge that pass through, I'm going to give it 6 joules of energy. Okay, if we increase the voltage of the battery, okay, means I'm providing more energy to each charge. Okay, you can take a look. As I provide more energy, now it's 55. That means every charge that pass through, every 1 coulomb of charge that pass through, I'm going to give it 55 joules of energy. So with a higher amount of energy, this charge will move faster and the current will be higher. The charge will move faster because of more energy. So the volts is similar to the, you can think of it as the energy in the circuit. Okay, that's it. That's the end of part 2.